Okay. Okay, then let's restart. And sorry again. So thank you everyone for being here. Today we'll talk about the galactic journey of the solar system through the Milky Way. And before answering the question, what is the environment that the sun encountered in the past? I would like to try to answer these other questions, which is what is the location of the solar system in the Milky Way? And first of all, I would like to start with a picture of a galaxy. So this is not our Milky Way, and is another galaxy which is called NGC 628. And as you can see, this is a spiral galaxy, probably similar to the Milky Way. And this is invisible light. So if we would look at this galaxy with our eyes, we would see this galaxy in this way. But actually, we have also other wavelengths using our telescopes. And the same galaxy in another wavelength would look like this. And so just to show you, these are two different wavelengths. And this picture was taken by the Hubble Space Telescope, and it is in visible light. And here you can see these brownish patches, and this is dust, dust and gas. And instead here you can see the same image, the same galaxy taken with the James Webb Telescope. And in this case, what you can see here in red orange is the dust and gas, which pops out way better than the other image. Why I'm showing you this picture? Because you can see here that, for example, we have some structure and some bubbles. So this is just an example of one bubble that you can see in this galaxy. And this will be important later for for the talk. But how usually bubbles are formed? Because we have stars, and some of these stars are massive stars, like, for example, this one. And when they end their life, essentially they go supernova. So they explode and they inject a lot of energy inside the interstellar medium, so inside the galaxy, and they push the gas away and they create these kind of bubbles. And as you can see from this picture, this is not a unique feature, but we have a lot of bubbles. So for example, here I'm just showing you some of these bubbles. And then you have also straight structure. This is another important thing that we have to keep in mind for this presentation, that we have bubbles and straight structures in galaxies. And another thing that we have to keep in mind is that this is just a photo of a galaxy, but in reality, galaxies are not static environments. So this is a simulation. So this is not a real galaxy, but this is a simulation of a galaxy. And you can see that over time, so this simulation runs for some million years, over time, this galaxy evolves. And all the gas that you can see here rotates around the center of the galaxy. So what about then the Milky Way? So does the Milky Way look like? Well, we actually don't really know how the Milky Way looks like, and this is the reason why. So this is the galaxy that I showed you before, just now in the previous slide. And this is Vienna seen from above, right? So, and why we can do this picture of Vienna? Because we imagine that you are on a plane, then you can see the city of Vienna from above. And you can take a picture, and then you can already see in this picture where there is the center of the city, where there are the outskirts, and how the city is organized. And the same thing we can do for other galaxies when we look at them from the Milky Way, so from our position. But instead, for the Milky Way, we cannot do such a picture because we are inside the Milky Way. So it's something like this, for example. No? So if we are inside the Milky Way, it's like we are in the middle of the city of Vienna and we took a picture of what surrounds us. It would be very difficult for us to understand what is the structure of the Milky Way from inside the Milky Way. And indeed, if you look around from Earth, you would see something like this. So this is just, if you look in one direction, you would see some clouds, and this is what we see. So it's really difficult for us to know the structure of the Milky Way, but we know some stuff. So it's not that we don't know anything. And so, for example, if you imagine an artistic impression of the Milky Way, you would see something like this. And the sun is located more or less in the outskirts of our galaxy and around 27,000 light years from the center of the galaxy. And moreover, recently, thanks to a satellite, which is called Gaia, for the first time, we were able to unveil the 3D structure of the local Milky Way. So not of the full Milky Way, but just of the stuff that is really local to us. And it would look like this. So I know that seems a very small patch compared to the full galaxy, and it is very small, but in reality, this is already a lot, and this is something that 5 years ago we didn't have. And so if we zoom in, we would see something like this. So here you see essentially the local, the solar neighborhood, so what surrounds us, and you see the sun at the center. So the sun is this yellow dot, which is sitting at the center. And you see that it is sitting at the center of an empty environment. So here, so the whiter the image is the more dust and gas you have. Okay, and so you can see, for example, that the sun is sitting inside the empty void, and you see also that we have straight structures. So these structures are like the ones that I showed you before in the first picture, if you remember. And obviously we give name to this structure. And for this talk, one name is this one, so it's the Redcliffe wave. And later I will talk about this structure. And the sun, you can see also that it's sitting inside a void, as I was saying. These bubbles are created by supernova explosions. And our bubble, we call it the local bubble. But in reality, there are also a lot of other bubbles around us. And in reality, the local bubble is not empty. But if you would zoom in inside the local bubble, inside this cavity, you would see that the sun, in reality, is going through a very fluffy environment of very low density clouds, which are called the local interstellar clouds. But again, this is just a snapshot of, yeah, sure. This is just a snapshot of the current situation, but in reality, the sun is traveling through the galaxy and essentially it takes around 225 million years to complete a full cycle of the galaxy. But again, you have to keep in mind that the sun is traveling through the galaxy. The galaxy is a constantly evolving environment, and also the other stars in the galaxy are moving, as I showed you before in the simulation. And for example, just to, if you can see this with your eyes and using real data. So this is in the background, you can see essentially our Milky Way as we see it from the Earth. And each one of these points is a star in the Milky Way. And now, in this moment. But since, thanks to Gaia, to this satellite that I told you before, now we know the position of the stars and the velocity of the stars. And so we can know how they will move in the future and also in the past. And this is the motion of the stars in the next 1.6 million years. So just to remind, the sun, it takes 225 million years to complete a full cycle. And here I'm just showing you 2 million years of motion of the stars. So this essentially just to keep in mind that the galaxy is a constantly evolving environment and everything essentially is moving. So the constellation that we see now in the sky were not the same 1 million of years ago and will not be the same in 1 million of years from now. And so from this first part, I just would like you to take away this, essentially that, again, galaxies are a constantly changing environment. We cannot see how the Milky Way is because we are living inside the Milky Way. So we were able just recently to unveil the 3D structure of the Milky Way, and then that the sun is located in the local bubble, and inside the local bubble, it is located in what is called the cluster of local interstellar clouds. And then as the other stars also the sun is orbiting around the center of the galaxy. And so now the next question, now that we learned this, is this one. So what is the environment that the sun encountered in the past? And sorry. So what is this environment that the sun encountered? So first of all, I want just to go back to this picture that I showed you before. So this is the local structure of the galaxy that is surrounding us. The sun is sitting at the center, and we see these structures. We know that the sun is moving through the galaxy. So the question that we can ask ourselves is, did the sun interact with any of these structures? And so just to make a zoom in, so we know that the sun is there. We know that the motion of the sun is coming from this direction. So if you take the velocity of the sun, the position of the sun, you assume a Milky Way potential, then you can go back in time. So you can rewind the orbit of the sun at least for 20 million years. After that point, the uncertainty is so big that we cannot say a lot. But for 20 million years, we can go back in time, and we know that the sun is coming from that direction. So it's kind of is hinting us that the sun is might have come or might have passed through the Redcliffe wave, so through this straight structure that I showed you before. And so what we did essentially to do this study that I did here with my colleagues was to consider essentially clusters. So what are clusters of stars? Are families of stars. So each one of these points is not a star, but is a family of stars. So it would look something like this. So each one of these points is not a single star, but is a multitude of stars that they are all born together. And so what we did was to use these stars, since we know their velocities, to use these clusters, so these families of stars, since we know their velocities, to see if the sun interacted with the Redcliffe wave. And what we did essentially was to take the Redcliffe wave clouds. So this is the Redcliffe wave. So we took the clouds of the Redcliffe wave. So each one of these points now is gas. Then we took the family of stars, and then we selected only the stars that we are, only the families that we like, essentially the families that we know might have crossed the motion of the sun. I know that, I hope it was clear, but if not, I will continue repeating. So essentially, the sun is the yellow dot. Then in red, you have the Redcliffe wave clouds, so the gas. And in blue, you have the families of stars that are associated with this gas, okay? And this is just another projection of the same thing. Again, you have the Redcliffe wave, the sun, and this region here, which is Orion. And you might know Orion because it's a very famous constellation that you can see, for example, in winter here, and you can recognize it. So when you look at this constellation, we are talking about a part of the Redcliffe wave, which is important for us today. And essentially what we did is this one. We know now where the sun is, we know where the family of stars are, and then we go back in time. And so essentially we rewind the orbits. I just play this back and forth. So there is the sun, we know where the families are, and then we go back in time, and then we try to understand if the sun was very close to these families of stars, and it was then passing through the Redcliffe wave. And so this is what we obtained. So this is the situation 20 millions of years ago. And you can see here in yellow the sun. Then you can see in blue the families of stars. And if a family is not born, we substitute this family with a sphere of gas. So in gray, you have to imagine that the gray is gas of the Redcliffe wave. And then you can see that around 18 millions of years ago, the sun is entering the Redcliffe wave. And then it is passing essentially through the Redcliffe wave. So now the sun is fully immersed inside the gas of the Redcliffe wave, of this structure that I showed you before. And then around 11 millions of years ago, it exits the Redcliffe wave, and then it continues its path through the place where it is now, so inside the local bubble. So what is the takeaway of this first essentially path of the sun? is that the solar system crossed the red cliff wave in the Orion region around 14 millions of years ago. And around 11 millions of years ago, it exited the red cliff wave. So it exited this region. Now we know that the sun is now sitting at the center of the local bubble, right? I showed you before where the sun is sitting now. But the question then is, when did the local bubble form and when did the sun enter the local bubble? Because the local bubble was not born when the sun was, for example, entering the red cliff wave. And so this is the situation. So we know that around 15 millions of years ago, the sun is outside the local bubble, is going through the red cliff wave during its path through the galaxy. And in that exact moment, during that period, we have some families of stars that are born, and you have a lot of stars. Some of these stars are very massive, and then they will go supernova. So around 15 millions of years ago, these stars go supernova, so they explode, and they inject a lot of energy in the local interstellar medium, and they push the gas away. And so the local bubble essentially was born. So the bubble in which we are living now was born around 14 millions of years ago. And we know that the sun around 14 millions of years ago is exiting the red cliff wave, and now it's continuing its path. And also the local bubble is forming. So essentially this bubble that was created by supernova explosions, so this, you have to imagine that some stars essentially exploded and they pushed the gas away, and this bubble is constantly essentially growing while the sun is going through its path through the galaxy. And then around 6 millions of years ago, essentially the sun entered entered the local bubble. So 6 millions of years ago, we were outside the local bubble, and around 6 millions of years ago, during that period, it crossed the edges of the local bubble, and we entered the local bubble. And then it continues its journey through the local bubble, but since in the local bubble there are still stars, some of these stars continue to die, and some of these went supernova, and so they continue to inject energy and to power the expansion of the local bubble. And till to the present moment, that the sun is essentially sitting at the center of the bubble. So the key takeaway of this other part is this one, so that essentially the local bubble started to form around 14 millions of years ago when the sun was inside the red cliff wave, and then the sun entered the local bubble around 6 millions of years ago. And then you have other supernova explosions that happen inside the bubble and that supported this expansion of the bubble. And now, as I told you before, we are sitting at the center of this cavity, but in reality, we are going through the cluster of local interstellar clouds. And now, so the question is, when did the sun enter this cluster? And this is another video made by Vanier. So essentially the sun here is this cross, this black cross. And here you can see the profiles of these very fluffy clouds that are inside the local bubble. And here is a very zoom in. So we are very inside the local bubble, as I showed you before. So it's something very close to us, and also something very close to us in time. So we are not talking anymore about millions of years, but this is the situation 300,000 years ago. So very, let's say, close to us, probably when Homo sapiens was starting to develop. And just to set a reference. And you can see that the sun essentially is moving, and around 150,000 of years ago, it entered these fluffy clouds, so these very low density clouds, to reach the position that it has now at 0, 0 in this plot. So here, and then in the future, it will continue to cross these clouds, and at some point it will exit this cloud and still continue its voyage through this local bubble. So this is essentially the other takeaway that I wish you keep in mind, so that the sun is currently moving through the cluster of local interstellar clouds. and it entered this cluster of local interstellar clouds in the last 150,000 years. So something which is really essentially recent and close to us. So now I hope this is kind of clear and you have a clear picture of what was the environment that the sun encountered in the last 20 million years. So it encountered the Redcliffe wave, it exited the Redcliffe wave, and then it entered the local bubble, and then it entered also the cluster of local interstellar clouds. Now, the next question then, which is a question that tries to connect astronomy with geology, is this one. So did this leave traces in geological records? So can we see some traces, some hints in geological records that can be explained only using astronomy? And I mean, the answer is yes. But before answering the question, I just have to introduce the two elements that we will focus in this talk, which are beryllium and iron. These are important elements for geology and for connecting geology and astronomy. So beryllium, well, it has like 11 known isotopes. Only beryllium-9 is stable. And instead here we are interested in beryllium-10. So beryllium-10 is an isotope of beryllium, and it has a half-life of 1.39 megayears. And the important thing is that one of the ways in which you can produce beryllium-10 is, for example, with high energetic particles. So these high energetic particles arrive, they hit the Earth atmosphere, and then you produce beryllium-10. And so one of the ways in which you can, for example, think of how can you produce more energetic particles is using a supernova. So if you have a supernova, which is close enough to the Earth, you would have more cosmic rays, so more energetic particles that arrive on Earth, and so more beryllium-10. So this is one way in which beryllium-10 tells us something about astronomy. And then another element is iron, and in particular, iron-60. So iron-60, why is important for us? Because it is heavily produced in supernova explosions. So you would not, so iron-60 again has a half-life of 2.6 million years. So all the iron-60 that you see on Earth is coming from outside, because since the Earth has some billion years, all the iron-60, the original iron-60 that was deposited on Earth when it was formed, is already decayed. So we should not observe it. But if we see it, it means that it's coming from outside. And since it is produced in supernova explosions, if we see it, it means that iron-60 is coming from some close supernova explosions. But then, so how are iron-60 and beryllium-10 delivered to our marine archives? You have to imagine that you have iron-60 and beryllium-10 in our atmosphere. Then you have some rain, and the rain brings these atoms down to the sea surface. Then you have some ocean circulation going on, and then these atoms of iron-60 and of beryllium-10, they just get mixed with the water. Some of them, they are absorbed into particles, and then they deposit into geological records. And then you have some geological expedition, and then essentially they dig these sediments out of the ocean floor, then they study these sediments. And how do these sediments look like? They look like something like this. So here on the top, you can see marine sediments. So this is, you can imagine it as kind of a mud. And instead, then you have also ferromanganese crust and nodules. And this looks like more, imagine like rocks. Okay. And an important thing about these two different types of geological archive is this one. So is the sedimentation rate. And this is important because this will give you the time resolution of the geological, essentially of your geological archive. Because For sediments, you have essentially these sediments grow 10 centimeter every 1,000 years. So you have you wait 1,000 years, you will have 10 centimeters of more mud. But instead, you have to wait 1 million years to have just 1 millimeter more rock. So the resolution in time is way different between the two of them. And this will be important later, or at least for some of the things that I will talk about. And then another way or another geological thing that you can analyze is snow in Antarctica and ice cores. So you can go to the Antarctica, you take some snow, and then you bring the snow to your laboratory, and then you analyze this snow looking for example, iron 60. And so, what are the results of this study that people have done? Let's start with the snow in Antarctica and these marine sediments. And with iron 60, and with a period very close to us. So here I'm showing you millions of years, but what I would like to talk first of all is something very close to us, so the last 50,000 years. And so, as I told you before, iron 60 should not be here because all the iron 60 that was originally deposited on Earth should be gone because it is a radioactive element, and so we should not observe it. So if you imagine that here on the y-axis you have how much iron 60 I have, I should obtain 0. So I should see a flat line. But in reality, what happens, for example, studying snow in Antarctica. So they took the snow of the last 20 years, so something very close to us, and they see that we have an excess in iron 60. So what does this tell us? That we have now iron 60 raining on our heads, essentially. So while we are talking here, there is some iron 60 coming inside the atmosphere and depositing in Antarctica, for example, in the snow. And this was a result of analyzing snow of the last 20 years. Then another study took instead sediments for the last 33,000 years, and they also see that there is an excess in iron 60. And then they analyze the last 80,000 years, and they see that there is not any more iron 60. So this is telling us that around 80,000 years ago, there was no iron 60. Then we probably were in a region where there was more iron 60, and that's why we see this excess. And we continue, and also now we see this iron 60. So we are still in a region where there is iron 60. And later I will guide you through the path of the sun and this excess that we see. But before doing that, instead, I want to show you what are the results if we use the ferromanganese, so this other type of geological record. What are the results in this case? So, as I told you, this has a very slow growth rate, but this means that we can go back a lot of time. And the iron 60 looks something like this. So again, we should not observe iron 60, but in reality, we see that we have two excess of iron 60. So we have two anomalies, two peaks in iron 60 that should not be there. And the question is, why do we see them? What was happening in that moment for which we can explain them? And then the other element that I introduced you was beryllium-10, and also here we see an anomaly. So again, we should not see anything, but around 10 millions of years ago, we see that we have an excess in beryllium-10. And so the key takeaway here essentially is this one. So that there are geological record anomalies that might be related to astronomical events. And so how do we explain these anomalies? So what causes this anomaly? And so again, this is the timeline. We know that since these elements like iron 60 and beryllium-10 have very small half-lives, we cannot probably go so far back in time. And during this period, if you remember, the sun was going through the Redcliffe wave. So we will not be able to see, at least for now, with the instrument that we have now, we will not be able to reveal iron 60 or beryllium 10 for a period which is older than 11 millions of years ago. But that's the period when the sun was going through the redshift wave. So probably we will have to use some different geological records to study this period and to see if the sun going through this structure left or not some visible signatures. And then around 10 millions of years ago, we have this beryllium-10 anomaly, no? And if you remember, I told you that one of the possible way in which you can produce beryllium-10 is via supernova explosion, because you can produce beryllium-10 if you have more energetic particle in our atmosphere, going against our atmosphere, and one of the way to have more energetic particle is to have a supernova explosions. And around 11 millions of years ago, the sun is exiting the redshift wave, but it is leaving behind very massive stars, which are ready to explode in supernova. And what we did was essentially to compute the probability of having at least one supernova explosion. And you don't have to go through this plot, but essentially here is on the x-axis, you just have the distance between the sun and the stars. So this means that they are very close, and it means that they are farther away. And on the y-axis, you have the probability of having a supernova explosion. And you can see, so the takeaway from this picture is that the probability is different than zero. So one of the possible origins of this anomaly might be astronomical. So we still don't know because there are other explanations, but the astronomical cause essentially cannot be excluded because you have massive stars and the probability of having a supernova is different than zero. Then, if you remember, we have another anomaly, which is around 6 millions of years ago, of iron 60. But around 6 millions of years ago, the sun was entering the local bubble. The local bubble is produced by supernova explosions. So in the walls of the bubble, you might have iron 60 because a supernova explosion produces iron 60. Iron 60 is ejected, and then the gas is pushed away, and the iron 60 is accumulated inside the walls of the bubble. And so the sun, when it goes through the walls of the bubble, it might acquire iron 60. And that's why we think there is an iron 60 anomaly when the sun entered the local bubble. Then we have another iron 60 anomaly that I told you, which is around 2 millions of years ago. But if you remember, around 2 millions of years ago, we have some supernova explosions happening inside the local bubble. And so again, you have some supernova explosions. So you have a shock front of the supernova, which is carrying iron 60. And then the sun goes through this shock front and essentially, again, eat some of this iron 60 that we can now see at the bottom of our ocean. And then the last one is this very recent iron 60 anomaly. So this iron 60 that is raining on us while we are talking now. And again, if you remember, around 150,000 years ago, the sun entered this local interstellar cloud. And we think that this is a nice explanation for explaining essentially this other anomaly of that we see in geological records. And then I'm almost done with the talk, so I was just going through the next steps that we are thinking too. So the idea is that we want to statistically characterize then the galactic environment that is encountered by the sun. So since we know that we cannot go a lot back in time, just 20 millions of years, the next step will be to try to answer a question, for example, how many times does the sun go through a given density in one full orbit around the galaxy? Then we want to better constrain the position of the sun over the past 20 megayears. So redo the study that I showed you before with the upcoming data that will be released soon, that will be available soon. And then also to look for other possible signatures in geological records that might be with which we can explain and see if there are any other connection between geology and astronomy, and yeah, also looking also in other radionuclide records. And as a summary of the talk, or I think the key takeaways that you should have in mind are these ones. So what we learned? We learned that the galaxies are a constantly changing environment through which stars are moving, that we cannot see how the Milky Way looks from the outside because we are living inside the Milky Way. But luckily, thanks to Gaia, so the local 3D structure of the Milky Way was unveiled. And so we know that the sun now is living at the center of a bubble, which is called the local bubble, and that we have straight structure, for example, the Redcliffe wave. And then we reconstructed the past environment that the sun went through in the last 20, 15 millions of years ago. So the sun was inside the Redcliffe wave, then it exited the Redcliffe wave, and then leaving behind very massive stars. And this might have generated this beryllium-10 anomaly. Then the local bubble started to form, and then the sun around 6 millions of years ago entered the local bubble. That's where we have the oldest peak in iron 60. Then the sun was inside the local bubble. Some supernova explosions happened, and then we have another signature in iron 60. And then we reached the current location by entering the local interstellar clouds, and we see now iron 60 raining on our heads. And yeah, the next steps I already told you. So I thank you for the attention, and I'm happy to answer any questions. And I think you have to advertise this also. I don't know. Okay.
First, we stick to the topic. Are there any questions?
Why is it in the center of the local bubble?
What is?
Center.
Mm-hmm. No. Neither a black hole or neither a neutron star. There is now the sun close to the center of the local bubble, and there are some very fluffy clouds, like the one that I don't know, like the one that I show you. Let me see if I found the slide. Yeah, like here. So the sun is sitting more or less at the center of the local bubble. Inside the local bubbles, there are other stars. And then, in particular, the sun is going through this very low density region of the local bubble.
Thank you, fascinating. I feel dizzy moving in this galactic carousel.
Yeah.
But I understood correctly, the local bubble circulates around the center of the galaxy as
Yes.
well.
Yes and no, in the sense that yes, it is moving as all the gas is moving around the center of the local bubble, around the center of the galaxy, sorry. But also it is constantly, the environment is constantly changing. So the bubble 15 millions of years ago, which is a lot in our, let's say, human lifetime, but is a small amount of time, the local bubble was not here. And if you imagine some stars explode, you form a bubble, and then you have galactic rotation. So these bubbles start to be deformed, and maybe you have some other supernova and the bubble disappear. And you can see this. So if you if you choose one of these bubbles, you would see that it is created and at some point it disappears from these simulations. And this, I think, makes a really nice visualization of how bubbles and straight structure evolves.
And if I may, the exoplanets we read about are inside this local bubble.
I think yes.
Plans on exoplanets being similar to the Earth. Are they in the local bubble or are they somewhere else in the galaxy?
So I think they are very, very close in the sense that the local bubble is around 300, from 300 to 600 light years from the sun. So obviously you have stars both inside and outside the local bubble.
So
but
inside and outside.
But yeah, stars are everywhere in the galaxy. So you have both stars inside and but stars outside. So looking from a perspective of the galaxy, the local bubble is really small. But looking from our perspective, if you look to exoplanet, they should be close enough. So the star hosting exoplanet should be close enough such that you can see the exoplanet. So they are inside the local bubble, these stars. But also other stars outside have planets, but we cannot see them. Yeah, exactly.
So first of all, thank you for the now you can speak for everybody. It's amazing. My question is, you saw the spikes from the beryllium 10 and iron 60, and we saw also the journey of the sun with it entered the local bubble and local clouds. But what does it mean for the Earth? Does it have any effects on, I don't know, maybe weather or something like that?
So thank you for the question. I would say that maybe so if you go through a denser region of the galaxy, you would have more dust incoming because you are going through a denser region of gas. And imagine like a plane in I don't know, an empty sky, or a plane going through a thunderstorm. No, so obviously it might. So obviously the environment changes, and the environment is important. I would say that up to now, we don't really know, but probably it has a minor effect or not even an effect. And yeah, I think this is a very interesting topic, but on the other side, very slippery. I don't know how do you say, because like there are some people that claimed that the sun going through the galaxy, this would cause ice ages, but this is a very, since I mean there is the climate crisis going on and a lot of scientific denialism against this. Some people are using this to just say that the climate crisis does not have a human implication. No, so that's why I think people do not like to discuss a lot maybe on this, but I would say that the effect might be, so if you go through an extreme environment, meaning if you go through a very, very dense region of the galaxy, probably is a minor effect. So yeah.
So I would have a question about whether there was even like close account between the sun and the different stars during its journey, and whether there's a chance in the future that it might collide, if it's possible, with another star.
Okay, so I think that the stars are, I mean, so about the collision, I don't think it will happen, in the sense that stars are really, really small compared to the environment, so to the galaxy. So it's like, so it's like they are going through, imagine an empty environment, and it's really rare that probably even, I don't know, it's more possible that two stars come close to each other, and then gravitationally they start to be bound to each other. And then at that point, depending on the type of stars, you might have an evolution of them. So one might go supernova, or they might merge if they are close enough and you have some gravitational waves emission. But two stars that are going around and just, I don't know, hit each other, probably not. Regarding I think they're called stellar flybys, so meaning that you have two stars and they come close enough to have a gravitational interaction. This happens, and essentially what happens in this case might be depending on how far are the stars, but the orbit of the stars changes. So they have maybe some gravitational kicks, so they change the direction and the orbit because you change the velocity of the star. And you might have also some perturbation of the Oort cloud, which is this cloud of objects, of rocky objects around. And yeah, this I think is, and there are, I mean, I'm not dealing with this, but I know that there are studies that studied the flybys, meaning which are the past stars that were very close to us and which are the future stars that will be very close to us. But I don't know a lot about this.
And how many galaxies are there? Billions?
Too many. I don't know. I don't know. Maybe someone else can help me.
Some numbers passed around.
Yeah, I don't know, but billions. Yeah, I would say. Yeah, I don't know.
So my question is, since we have the straits that you showed, wouldn't we expect to see a lot more like chaos with stars going supernova, but not? Why do we see like those straits which have like way more stars, so way more supernovas should be happening there, right?
So if I understand well, so we see straight structures in for example, in the solar neighborhood, but we should also have a lot of supernova. So the question is why we have why we do see these structures and not is a chaos, right?
Yes.
Okay. So I think why these structures have this, for example, this orientation, how did they form is still an open question and open research point. But the idea, so there are different ways in which you can explain this. So, but for example, again, I think one thing that is important to keep in mind is the scale that we are dealing with. So I think this bubble here, this giant bubble here that you see here, was probably generated by 100, 120 supernova. So you had a lot of supernova, but obviously you have also a lot of gas that you have to push away. And it's not that the gas disappears, the gas just accumulates. And so you will imagine that if you have a family of stars going in this direction, no, then they explode supernova, they push the gas away, and then all this gas get accumulated, for example, on one side. And this is one way. And at the same point, you have also the galactic rotation. So things get stretched, and so you form these kind of straight structures. But then this straight structure will probably, again, be destroyed by some supernova, and this is kind of a process that, in a sense, continues.
Would that possible that there will be such gravity assist that we will be kicked out of the Milky Way?
Well, I know this so strong, I don't think.
You have shown here the movement of the stars within the Milky Way.
Yes.
And based on that, you have done the observation. Currently, do our instruments have the resolution to produce such a simulation on some other galaxies?
Well, I'm not sure, but we have simulations about, for example, so we have. Okay. So the problem about simulation is obviously the memory and the computing power that you need for a simulation to run, essentially. And so we have, for example, simulations imagine from the universe, so cosmological simulation, down to sub-parsecs, so very small so from cosmological simulation to planet simulation, okay? But obviously, what we talk about when you use simulation is about resolution. So in a cosmological simulation, you don't have you have a resolution, but is very big, you know? So you don't maybe have a resolution of a Milky Way, imagine. So each point in the simulation is like a Milky Way, or maybe is like 100,000 sun. Okay, so it's a very, I mean, in a cosmological simulation is very small, but in reality is very big compared to what we would like to know. Then you have simulation that just focus on galaxies. And in this case, you have a better resolution, but still having a full simulation with, I don't know, light years, with maybe AU, so astronomical unit resolution is still impossible in a sense. So what they do is that they take the full simulation and then they think, oh, this area of the simulation is nice, and then they increase the resolution just in that area, but not the full simulation with super high resolution. Yeah. I hope I was clear.
Yes. And the question, you are talking about gases inside the bubble. Which type of gases? Yeah. Natural flavors.
So is mostly is hydrogen and helium, and then obviously when you have a supernova explosion, this the supernova produce what we call metals. So whatever is so in there is hydrogen, helium, and then astronomers calls all the rest metals. So all the other elements are produced in supernova, and then they are released in very tiny amounts compared to the rest of the gas inside yeah. But mainly it's hydrogen and helium and a bit of dust. That's why when you look at the galaxy, you see this. So this brownish stuff is dust, meaning elements which are not helium and hydrogen.
First of all, thank you. That was really interesting, the session. So maybe I have a general question, because you mentioned a lot of studies and backdating the time and everything using the isotopes like Fe60, right? So
yes.
Is there any other isotopes that maybe extraterrestrial isotopes or maybe rare type of thing that we can use to do the similar kind of study, which can also come out from maybe strong energy dissipation or something like that?
Yes.
Or is it too long? The half-life is too large, we cannot trace it.
So there are other, so I'm not an expert in this, probably my answer will be just half true, but there are other elements that, other isotopes that people can use, but they come with problems. So for example, you have another element is plutonium, which has a, I don't remember now the half-life, like 80 million years, maybe I'm wrong, but way bigger than, let's say, iron-60. But plutonium, for example, have two problems. One is that obviously the time resolution, so the half-life is bigger, but then this means that the time resolution is lower, because if you have an atom of plutonium, then you don't know if it is if it was produced now or 80 millions of years ago, no, right? Because it lives a lot. Instead, if you see an atom of iron-60, you know more or less that it should be close to us. And then plutonium, the other problem is that it's not produced as much as iron-60, and is way more difficult to produce it. So you would have way less plutonium around than iron-60. And then, for example, you have other elements like aluminium-26, and the problem of these elements that are produced also in supernova explosions is that they are heavily produced by cosmic rays, so by these energetic particles. And so there is the background is very high. So you cannot, so imagine maybe a supernova produce 10 atoms of, now just say a number, of aluminium-26, but then cosmic rays produce maybe 100. And so you don't know what is what. Instead, is the opposite way for iron-60. So you know for sure that the main way is supernova. I think there is a, yeah.
Showing that the progression of the galaxy is pretty sporadic and chaotic. And then you also show a slide with our solar system going in a direct circle around our galaxy. Is it a realistic assumption to say that we go in a circular pattern around our galaxy, or do we maybe also take like a more elliptic revolution around our galaxy?
So I would say that is not maybe super realistic over billions of years. So yeah, obviously the sun goes through the galaxy, then it will also gravitationally interact with things. So for example, if you go through the redshift wave, probably you would have some gravitational pull, so your orbit will change. And also there is this thing called the stellar migration. So usually stars migrate during their life inside the galaxy. So they are usually, so if you are born, for example, around, I don't know, in around 10,000 light years from the center, then during time, due to these processes, the star will migrate towards the outside of the galaxy. So where we are now, probably we were not born here, essentially, but we were born more inside the galaxy. And over some billions of years, we just drift outside.
Yeah.
Right.
Let's go.
Yeah.
In April, we will get an update on the Extremely Large Telescope from Kieran Nishinsky. Our last talk on the Extremely Large Telescope was 4 years ago. At the time, we could only show computer renderings of the telescope. This is a recent picture of the construction site. It's close to being finished, and in a few years' time, it will start operations. So in April, update and more background information on that. As I always say, that's going to be the largest telescope in the world in a few years' time. And if you want, you can join Meinrad Hafner and me now up to a former largest telescope in the world. We will see whether we can see something in the sky. Right? So we meet at the Meridian Circle just outside the USA in a few minutes' time. Otherwise, see you in April.